Unit 15, Equilibrium, and this is pages 134 to 146. The concept of equilibrium. A kinetic view of equilibrium. Chemical reactions take place in both the forward and reverse directions. When reactant R is added to a closed container, the rate of the forward reaction is faster than the rate of the reverse reaction. So when a reaction starts, you have mostly reactants, and so the forward reaction is going to proceed very quickly, and the reverse reaction very slowly. As the concentration of reactant decreases, the forward rate slows down. So the more products we make, the slower this reaction is going to become. Equilibrium is the point where the forward and reverse reactions are equal. So at some point, the forward rate becomes equal to the reverse rate. Reactants are making products at the same rate as products are making reactants, and it's both reactions occurring simultaneously. Equilibrium is dynamic. At equilibrium, the rate R to P equals the rate P to R. Both reactants to products and products to reactants, the forward and the reverse reactions, continue to take place. But since the rates are equal, there is no net change in the amounts of reactants or products at equilibrium. This condition is called dynamic equilibrium, which means the products is constantly being made and destroyed, but the amounts of reactants and products don't change. An analogy of kinetic equilibrium. So imagine a container where the fill rate equals the empty rate. This creates a steady state for the amount of water in the container. Water flows into and out of the container, but the amount of water held in the container remains constant. So notice we have water going into the container. Simultaneously, water is going out of the container. However, the level of the water that's in the container remains the same the entire time. So there's no net change in the amount total in the container, even though we have this filling at the same time as this is emptying. Dynamic equilibrium means that product is constantly being created and destroyed, but the amount is constant. The law of mass action. The equation that predicts the relationships between the amounts of reactants and products in the equilibrium mixture is called the law of mass action. The equation comes about because the amount of reaction for each ingredient is linked by the stoichiometry. So if you have this general reaction, A plus B yields P plus S, and they have coefficients of lowercase a, lowercase b, lowercase p, lowercase s, the concentrations at equilibrium are determined by the equilibrium constant K. And so the equation would be written as follows. K, the equilibrium constant, is equal to the products raised to the power of their coefficient multiplied to one another, and then all of that is over the reactants A raised to the lowercase a times B raised to the lowercase b, where P, S, A, and B, all lowercase, are the stoichiometry, and P, S, A, B capitalized are the concentrations. Remember that brackets represent concentration, which is in a unit of molarity. Note K depends only on stoichiometry and not the mechanism of the reaction. The equilibrium constant K determines the relationship between the amounts of reactants and products at equilibrium. This table shows a reaction with K equal to 1.5. At equilibrium, the values for reactant R and product P are related by the value of K. So what that means is, here's our reaction. Reactants yield 2P, and the equilibrium expression, or the law of mass action, would be K is equal to P squared over R, and the K is equal to 1.5. So that means that the K is constant, remains 1.5. Therefore, the amounts of reactants and products always have to equal the equilibrium constant of 1.5. And so you can see how the concentrations change. However, when you do the math in the law of mass action, you get 1.5 in each case scenario. K has no units. This is like a big star. You're going to be asked about this a few times. The equilibrium constant, no matter what, is unitless, has no unit. concentration equilibrium constants. So let's say you have this equation, and you're going to have Kc is equal to B squared over A. And you see the Kc here. I'll let you know that there are actually several values of K that you might see. You might see K by itself, Kc, which is equilibrium of concentration. You might see Keq, which is just means equilibrium constant. You might see Kp, which is equilibrium with pressures. Ka, equilibrium with acids. Kb, equilibrium for bases. And Ksp, which stands for equilibrium of the solubility product, which means equilibrium of a solution with an insoluble compound. The subscript C means concentrations in moles per liter are used, or molarity. So Kc means you're dealing in units of molarity. Square brackets indicate that concentrations in molarity were used. Pressure equilibrium constants. So here's the same equation. Note this is a gas and this is a gas. And so we would write Kp, which is the equilibrium constant dealing with pressure, is equal to the pressure of B squared, partial pressure of B squared, over the partial pressure of A. So here we're dealing in pressures as opposed to concentrations. The subscript P indicates that for gaseous species only, partial pressures in atmospheres are used. Here, Pa is the partial pressure of A, and Pb is the partial pressure of B. We can convert between Kc and Kp. The value of K depends on whether gas pressures or concentrations are used. In general, for the gas reaction, lowercase a of the gas yields b of the gas, where the change in moles of gas is, so delta N is the change in moles. You would take the coefficient of my product minus the coefficient of my reactants, the sum of all products minus reactants to get the change in moles. So you do final minus initial. So here's the equation. You have Kc, the equilibrium constant for concentration, is equal to Kp, K for pressures, times RT raised to the negative delta N. And above we described how you would find the delta N. Remember, it's for gases only. Or you could find Kp by taking Kc times RT raised to the positive delta N. R is going to be the gas constant, 0.0821 atmospheres liter per mole Kelvin, and the temperature must be in Kelvin here. Example 15.44. Write the equilibrium constant expression Kc and Kp for the following combustion of ethane. So let's write the Kc first. Kc equals, we'll take our products, put them in brackets, CO2, and raise to the power of the coefficient. So it's going to be carbon dioxide squared times water cubed, water raised to the third power. So products over reactants. Now I'm going to put in the denominator C2H6 or ethane, and that's raised to the first power, times oxygen O2 raised to the second 7/2 power. If I wanted to write this in terms of gases, I would write Kp equals, we do not use brackets, we're going to use parentheses. So first I'm going to write a capital P, which stands for partial pressure, of CO2 because it's a gas, CO2, close parenthesis, and then square it because that's the stoichiometry here in the equation, times the partial pressure of water cubed, because of the stoichiometry, that's a gas also. Remember, you can only write these, include gases in a Kp expression. Put all of that over my reactants, partial pressure of C2H6 times the partial pressure of O2 raised to the 7/2 power. Example 15.45. At 300 Kelvin, this reaction mixture is at equilibrium. Find the equilibrium constant Kc. And the good news is we're given molarity, 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 and so it's already set to find Kc. If these would have been in atmospheres, then we'd only be able to find the Kp, and then we'd have to convert Kp to Kc using the equation. So first I'm going to write the law of mass action, or my equilibrium expression. Kc equals the concentration of ammonia squared divided by the concentration of nitrogen and the concentration of hydrogen cubed. Now I can actually input these values because these are the values at equilibrium. And so I'll say Kc equals, and 3.55 times 10 to the negative 3 squared divided by nitrogen and hydrogen cubed. Open parenthesis, 3.55 times 10 to the negative 3, close parenthesis, squared, divided by, open parenthesis, 0.12 times 0.10 cubed, close parenthesis. Notice that both of these are in the denominator. They are being multiplied to each other, but they both need to be in parentheses because this first number is being divided by the product of these two. I'm going to hit equals, and we get 0.105. Example 15.46, find the equilibrium constant Kp at 300 degrees Kelvin for the ammonia equilibrium using the given value of Kc. So recall that there's an equation we can use that relates Kc and Kp, and we want to use the one that solves for Kc. Actually, we want to use the one that solves for Kp, delta N. So now I can plug in my values. Kc is 0.105, and that's going to be times 0.0821 times 300 Kelvin raised to the, and now we need to figure out what's the change in moles. Remember, it's going to be products minus reactants, and it's of gases only. So we have 2 moles of gas as a product minus 3 plus 1 is 4 moles of gas as a reactant, which is going to equal a -2. So this is going to be a value of -2. Now we can type it into our calculator. Equals. We get a value for Kp equal to 1.73 times 10 to the -4. And remember, there are no units. Magnitude of equilibrium constant. What does the size of K indicate about the equilibrium conditions? For simple reactions where the stoichiometry is 1, a large value of K indicates that the amount of product is much larger than reactant. So there's mostly products and very little reactants at equilibrium when you have a very large value of K. Similarly, if K is small, then you're going to have mostly reactants, a large amount of reactants and a very small amount of products at equilibrium. When K is small, the equilibrium mixture consists mostly of reactants. Relationships between equilibrium constants, and there are 3. Number 1, the equilibrium constant for a reaction written in reverse, Kr, K for the reverse, is related to the equilibrium constant of K forward as follows. Kr is equal to the inverse, so 1 over Kf. So if I take Kr to the -1, then I would have Kf. So here is my forward reaction. Kf would be equal to P squared over R. Then if I wanted the reverse, then I would take the inverse of this, and so the reverse would be R over P squared. Reaction A below with equilibrium constant Ka is multiplied by a factor of 3 to obtain reaction B. The equilibrium constant for reaction B is the original equilibrium constant Ka raised to the power of 3. So if I take this equation and I multiply these coefficients by a number n, then that means that I'm going to take the Ka and raise it to the power of that value. So because these were multiplied by a coefficient of 3, or the coefficients were multiplied by 3, then that means this K would be raised to the 3rd power. 2 or more reactions can be added together to make a net reaction. So here, if I want to add these 2 reactions together to get this net reaction, because notice A and A would cancel, C and C would cancel, and I'd be left with B and E yields F and D. If you add 2 reactions together, then you're going to multiply their Ka values and Kb, both of their K values, to get the net K of the reactions combined. Example 15.47. Deduce the value of the equilibrium constant for the reaction 2B yields A. So what would be this K value given the equilibrium constant for this reaction? So first of all, I'm going to write my second reaction, which has a K2 equal to 1.5. And now I need to make some changes to change this reaction to this one up here. So first of all, notice that it's reversed. So if I were to reverse this reaction and make it B yields 1/2 A, then that means I have to take K2 and raise it to the -1. And so my new K is going to be 0.667. Now I'm going to take this equation, and in order to make it have these coefficients, I need to multiply all of these by 2. And that's going to give me a 2 here, and that's going to make this a value of 1. And then that would give me this balanced equation there. So because I'm multiplying this by 2, that means that I want to raise this K to the power of 2, or square it. So I'll take the 0.667 and I'll square that value, and I get a K equal to 0.444 repeating. And so that would be the K for this reaction based on this equilibrium constant for this reaction. Example 15.48, deduce the value of the equilibrium constant for this reaction. And you're given the equilibrium constants for these two reactions. So I rewrote those here. And first of all, notice what cancels. You have a bromine as a product here and a bromine as a reactant here, and so those cancel each other out. And what you're left with is 2 NOBr plus, so here, plus Cl2 yields 2NO gas, nitrogen monoxide, plus 2BrCl gas. So basically these two canceled, and this is my net equation, which matches this equation up here. So in order to get the K value for that equation, I simply need to take K1 times K2 to get my net K of the combination of these two equations. So I'm going to multiply 0.014 times 7.2, which gets me 0.1008. And that's going to be the K for this equation up here after we add these two equations together. Page 146 is basically a lot of stuff just telling you at the end that no matter what, the equilibrium constant K has no units. Now pause the video and copy down the contents of this note card. The following are true at equilibrium. Delta G is equal to 0 and delta S total equals 0. There is no net change in concentration of reactants and products. Product is constantly created and destroyed, but the amount remains constant. The forward and reverse reactions are both occurring at the same rate. Rates of forward and reverse reactions are equal. So all of these 5 bullet points are true statements of a reaction at equilibrium. K is the equilibrium constant, and it has no units. Variations of this constant are KEQ, KC, KP, KSP, KA, and KB. Brackets mean concentration in molarity, and capital P means partial pressure in atmospheres. We can convert between KC and KP using these two variations of this equation, where delta N is the moles of gaseous products minus moles of gaseous reactants. R is 0.0821. The magnitude of K gives you an idea of where the equilibrium lies. If you have a very small K, then there are mostly reactants in the equilibrium mixture. If there's a large value of K, there's mostly products in the equilibrium mixture. And so I like to draw little k, medium K, big K to kind of show me that a small K means there are mostly reactants and a large K is mostly products. Finally, you should be able to manipulate the equilibrium constants if I take Kr and I want to know Kf, I would take the inverse of Kr in order to get Kf. If you multiply an equation by a value n, then that means you're going to raise K to the power of that number. And if you add reactions together and get a net reaction, you would multiply the K's to one another in order to get the net value of K.